Thanks a lot for coming. So today we have a speaker, Nishant Mehta from University of Victoria in Canada. He's been visiting for roughly 2 months. Staying until next week. If there's anything you would like to discuss with him, he has an office, so we should be able to arrange a meeting. And Nishant's interests are probably in online learning nowadays, but he's been doing also quite a bit of work in statistical learning, fact-based, many different things related to theory of machine learning. And today's gonna be talking about his joint work with his PhD student Juan on staging bandits.
Okay, thanks for coming to my talk. Let me know if there's any volume issues or if I'm too loud as well. Is it okay? Okay, cool. Yeah, so I wanted to begin by mentioning, this work is, so Quan Yuan is my PhD student. He's brilliant. This is primarily his work. This is the first time I'm giving a talk where like my student pretty much like proves everything. And this work was mostly Quan is working on some problem. And there was a certain subproblem that he had that he showed me. And I was like, wait, that subproblem is basically what's the title of the talk now, right? So that I pointed to some literature, we discovered that these bounds, which I'll explain what these are, like throughout the talk, that these did not exist. And then gave some random pointers to like 2 or 3 papers from the last couple of decades. And then Quan like starts proving results. And then, as things progressed, we wanted to generalize things in some more general framework. And I thought it would take 2 months, and Quan within a few days managed to do this, right? So I was hoping we'd have some interaction over a few weeks and he'd be stuck and I could be an advisor and help, but he spoiled all the fun, which is very nice. I'm very proud of this guy by solving these things. Okay, so so I think that's, I want to make sure he gets credit for this. I'm going to introduce the setting by starting, that did not work, 1 second. Okay, I want to introduce a gambling problem. So I think people here, I don't know how familiar you may be with sequential prediction problems. So I'm going to encourage you to stop me. You can ask questions about the setting. We don't have to cover all of the material. It's better to gain something from the talk. But here's a basic setting. So we have a sequential prediction problem. Okay, it's going to take place over a number of days. And we're going to have, first, there's going to be a set of experts, right? So suppose we have maybe 3 experts, right? And there are going to be 2 players in this game. So there's a learning algorithm. What I want you to imagine is that in every round, the learning algorithm has some fixed sum of money, maybe like $100, and it's going to select one expert, okay, and give the money to the expert. The expert will secretly invest the money somehow, and the learning algorithm will get back a return. And in general, the algorithm might make money or it might lose money. We're going to frame things in a way where it might sound weird, but assume that the learning algorithm always suffers a loss. The loss could be 0, okay? But in general, it's going to be losing money. You can fix this by adding some bias, right, to each round, right? So maybe like a loss of 0 really means it gained $2, okay? You can add an offset. So in this setup, I want you to imagine that there are these experts. And on any given day, an expert might not feel particularly useful. They might not have any good intuition about investing on that day. Okay, maybe depending on the weather, maybe depending on recent world events. Maybe a war started the previous day. It refuses to give advice because it doesn't predict it's going to do well. So every day, these experts, each of them will decide whether or not they want to be available to give advice. Okay? And then the algorithm is going to select an expert that is available, okay? And then the expert doesn't reveal their strategy. There might be some reasons why it wants to secretly invest, okay? And then the learning algorithm, it only selected one expert, and it's only going to suffer the loss, right? It's only going to look at the performance of the expert that was selected, right? In a more general setting, or a nicer setting for the learning algorithm, it would suffer the loss of the expert that it selected. It would get the return back, right? But it would also see what would have happened, counterfactually, for any other expert that it might have selected, right? But we want to look at this setting. And in plain English, this is going to be the goal. So for each expert separately, right, the learning algorithm can only compare its performance to an expert in those rounds when the expert was available. Right? For other rounds, when the expert was not available, it didn't have any strategy. You can't talk about the lock of the expert. So for each expert separately, the learner would like its cumulative loss over only the rounds when the expert was available to be not much larger than the performance or cumulative loss of that expert. Right? This is something that we call the per action regret. You can imagine the expert is like an action, right? Each expert has an ID. Right? So, and the one fun thing for this talk, well, okay, maybe the other fun ones. So, does anyone know who these people are? Anyone
on
in
the
the
right.
Say what?
I know the one in the right.
Yeah, the one on the right's the most recent. So that's Sam.
The one on the left I've seen, definitely, but I don't remember.
Yeah. And then the one in the middle is the most famous, actually. Fonzie, yeah, Ponzi scheme. Yeah. So the experts can be. I want to stress that these experts, they can be adversarial. Okay. So they're not necessarily out there to help you, because we want to assume that we live in a world where maybe there is one expert which is very good, but you don't know which one that is, and you want to be robust to experts that are very nasty and that might make it difficult for the algorithm to lock onto the best expert, right? So have in mind that these are experts, they're very smart, scheming people, and their investment strategies might be adaptive. The learning algorithm in the previous round picked the first expert. That might influence the losses of the experts in the next round, right? So this is basically what we call a reactive adversary, sometimes also an adaptive adversary. I'm going to use the term reactive because the term adaptive will be used in a context in this talk. So before getting to the setting, I want to give you this this nicer setting for the learning algorithm formally. So this problem is called sleeping experts, okay? So we're gonna have two players. So nature is gonna be the adversary. You can imagine that nature is the one that is controlling the availability of each expert in each round. Okay, so nature is first gonna set an availability for each expert J in round T. It'll just be a binary value, 0 or 1. And then the learning algorithm is possibly using randomization, gonna pick an expert IT. You can imagine that IT is drawn from some distribution PT over the experts. And then nature is going to play some loss vector. This loss vector, it can depend on the entire history of the game so far, including PT. Not including IT, which is drawn from PT, right? But you can view PT as a mixed strategy, right? It's a distribution over actions on the part of the learner. And this loss vector can depend on that immediately previous choice, PT. So the adversary has a lot of power here. And then we're going to assume, as before, that the learning algorithm suffers this loss. If you want, you can imagine taking an expectation, right, around IT, because it's drawn from some distribution. And that's what we're going to use over here. L hat T, when the learning algorithm uses distribution PT, L hat T is going to be its expected loss, right? It's a dot product, basically, right, between PT and this loss vector. And the thing that's different from the example I gave you on the last slide is we're going to assume what we have is a full information game, meaning that the learning algorithm is luckier than the previous slide. It gets to observe all the components of this loss vector. Okay, so it's gaining all the information that's been revealed, right? It gets to see the availabilities, it gets to see all of those components. And formally, this per action regret is defined this way. So we're going to take a max over all of the experts. I write A because experts are like actions in this case. And then formally, this is the per action regret. So for a given expert A, you just look at those rounds where it was available when IAT is equal to 1, right? And then for those rounds, you compare the learning algorithm's expected performance conditional on PT, right? Minus the expert's loss. So this is like the key definition that'll be important for everything. So is it clear? Are there any like notational questions? This is supposed to be an I. Okay.
So we know, even if it wasn't available, we know how much loss each expert would have had.
Oh, sorry.
Although it
This
doesn't
is a good
doesn't
question.
go to both.
Technically speaking, an expert that was not available, I should put like an X.
It multiplies by 0.
Yeah.
So you don't actually.
Yeah. So technically, you only get to observe the components of the loss vector when an expert was available. Otherwise, the losses I don't even want to say zero, I want to say it's not defined,
Okay,
not defined.
fair enough, fair enough.
Yeah, but yeah, that's a good point. So, yeah, so if only the first two experts are available, you'll have, two losses in this vector, and then you'll have
Annex.
bot or whatever symbol you want, like some, not defined, right? Yeah, and because of that, anything we do algorithmically can only use losses that are defined, right? So that, unless there's a typo somewhere, we should only be using losses in any given round for experts that are available. Okay, that's not to say that we can't cook up our own losses for unavailable experts algorithmically and pump those into, some other strategy, but we'll get to that in a second, right? And the thing I want to mention without getting into any algorithm yet is that there exists an algorithm, which is nice, it's not hard. No, actually, this is somewhat complicated. There exists an algorithm that gets per action regret, right? So there's a max against all of these experts, which takes a form which is that there's one term which you'll often see in these situations with a game of full information where you want to compete with the best expert from some class of K experts. Okay. So this log K is standard. If all of the experts were always awake, then no matter what expert you had here, the sum would be capital T. And that is the standard bound in the game of prediction with expert advice, which is basically what I have over here, except when nobody ever goes to sleep, you get that. So what we get here is something, well, if a given expert was only available in some constant number of rounds, then you're going to get something much smaller over here. In these special cases where this summation is extremely small, I think you might need an extra plus log K on the outside. Okay, but this is like a good, this gives you the main idea of the bound, right?
So this regret bound you're writing is to compare against A.
Yeah, but then this is
If
yeah. I actually wrote a more refined bound, which would be for any A,
yeah,
for any expert, you would have a different bound for each expert, right? So one expert that's always awake, for that expert, you would have a T, capital T over here. For experts that are rarely awake, you would hope to be able to compete with lower regret against them, because there's very few rounds in the summation for the regret for those experts.
But
Yeah,
if I
so
wanna
this is
get
a more refined, I should say this more refined.
I mean, if I wanna get a uniform bound, I just take the maximum.
Yeah, but in this setting, you should not be happy.
You wanna
with that.
keep
You
this.
should go for the refined, yeah. But in general, for other stuff, I'm gonna be dealing with bounds on the max version. It's just like in this full information setting that you can say some nicer things.
And that,
Yeah.
L hat T, that is taken from the expected value.
Yeah, oh, and I want to be clear about one thing. So this distribution PT, in round T, that distribution should be supported on the available experts. Because you're not allowed to play somebody who's not awake because their loss is undefined. So you still have in mind, you're only allowed to pick an available expert. Picking an available expert with randomization means PT is supported on the set of awake experts or available experts. Throughout the talk, the references for like the key contributions for like a setting or whatever, they're always in the top right usually. So can share slides later if you want to have those. I want to talk a little bit about why should one care about this setting, and it might be a little bit more difficult to motivate this if you haven't had previous exposure to like these online learning problems with reactive adversaries. I don't know how much I can do about that, but what I will say is that if you're somewhat motivated about this general problem of every round experts are giving me advice. An expert could even be an algorithm, right? I could have K different algorithms that are taking in data in each round and they are adapting, right? They're possibly using predictions of other algorithms in the past, as well as the plays of the learning algorithm in the past to decide what they're going to offer as advice in the next round. That advice is not apparent in the protocol, but an expert's advice, you can imagine that it's some action that they could take, some particular investment strategy that would lead to some particular loss. And the algorithm in this protocol is only going to use the loss. It's not going to use the hidden actions of an expert. Okay.
And
So that
why are we only talking about losses? I mean, you mentioned something about the bias and you can make it a little gain, but why not just make it negative when you gain?
There are some technical reasons when we get into like games of partial information that being able to handle losses, we can do. Being able to handle gains, we can do. Being able to handle like losses and gains together, sometimes like certain Taylor inequalities, like you run into trouble and it's like a little bit more challenging. So I'll say that if you prefer to think of gains instead or like rewards, we
Well,
can
I
go ahead and
wanna
do that.
have them both.
Yeah, but if you wanna have both, then it's going to be a little bit more technically challenging. There are like many cases of results in this area where they do losses, they do gains, and I don't know necessarily, I'd have to look hard to find a paper that handles like the both of them.
Right. Fair enough.
It's kind of like an annoying technical issue, like fundamentally, you
Well-
shouldn't have to worry about like that case should not be difficult. Like it's,
Well, I mean, I would just like it to adapt to
Yeah.
real life, right? Because it would
Exactly,
be
yeah,
more, yeah,
yeah.
but it's fine, yeah.
yeah, but I'll say for this setting, right, maybe you can do the following, you can say that, well, if the algorithm, you know, pumps in $100 to the expert, you automatically assume that I want to imagine like adding some bias
You
to
have
the loss.
maximum bound
Yeah.
or something, and then loss is really loss plus something.
Yeah, something like
that.
Yeah, I think there is some kind of hack like that, Mike.
Okay.
But so, hopefully the first point I convinced you of, experts, it's nice that they have the freedom to decide whether they give advice or not. In the real world, experts might decide, in a certain round, I'm going to abstain. I don't have anything useful to say. Or maybe each expert, if you imagine that you are figuring out some problem, so there's a problem called online shortest path, where every day you're deciding how to go, let's say, from home to work along some graph, and edges have costs. And let's imagine that every path, right, in this graph, every path, if you take the sum of the edge weights, right, edge weights corresponds to travel time. The sum of the edge weights along a given path will give you the cost of the path. And then tomorrow, a given path might not exist because there's construction, right? So, you know, actions or experts can disappear and they might come back later, right? So in the real world, you want to entertain this possibility that you don't have access to all experts in all rounds. The thing that I find possibly even also interesting is that if you consider a classic setting where in every round, all experts are always awake, and you look at that notion of regret that I had from before, if all experts are always awake, what you're doing is you're comparing the learning algorithm's performance to the cumulative loss of the best expert in hindsight. But who's to say that you should only compare to the best expert in hindsight over the whole sequence of rounds? What if you run your algorithm and they say, well, I care about the performance of your algorithm on the middle 1/3 of the rounds, on the middle 1/3. It'd be cool if you could have a guarantee that would hold well for any interval of the rounds. And we'll talk about this a little bit later. It's called adaptive regret. You can get bounds for like the whole for any interval, right? For any contiguous subsequence of rounds. You can get those using the sleeping experts framework, right? So this is going to be a reduction idea. Tracking regret, I'll wait until we get there, but I'll explain this as well. It's another notion of regret, which is much more powerful than the one I've shown so far. This one I won't talk about at all, but it's like, take it offline if you want. So it's kind of related to adaptive regret. And so what I want to do now is, I want to convince you of the power of the sleeping experts framework. And here I'm going to be talking about old results, and hopefully this will give you motivation for sleeping experts, which is the full information version of this game. And then we're going to make the game harder, and we're going to make it so that the algorithm only gets to observe the loss of the single expert that it picked, right? And it doesn't get to observe the other ones. This is going to force the algorithm to do some amount of exploration so that it learns about alternatives that it hasn't tried before, okay? So adaptive regret is defined in the following way. So in plain English, right, I'm going to say that you compete with all possible intervals. What does that mean? So pick a given interval, right, starting from around T1 to T2. T2 could be equal to T1, right? It could be like maybe this blue region over here, roughly the middle 1/3 of the game. And then over such an interval, you would like to compete with the best expert in that interval, right? We still have the max over experts over here. So this is sometimes also called the interval regret. You would simultaneously, right? There's a max and a max. So for any choice of interval, for any choice of expert, you would like the learning algorithm's cumulative loss over that interval not to be much larger than that of an expert. Right? So this is quite powerful in particular because you might imagine situations where maybe there is something special about the first half of the game. In the first half of the game, maybe, actually, yeah. When we get to tracking regret, I'll have a good motivation for this thing. Right now, I'll just say that I hope you're intrinsically motivated by this ability to compete over intervals. In hindsight, somebody tells you, I only care about a certain part of the game. What guarantee can you give me? If you have a guarantee which holds over all of the rounds, that does not necessarily mean anything about the regret that you could have in intermediate intervals. Okay, so you have to be a little bit more clever in terms of algorithm design. So what I'm going to do now is show you how you can reduce sleeping experts. How you can reduce this problem of getting low adaptive regret, which, by the way, as a special case, there is the interval from 1 to capital T, right? So we're strictly making things harder for ourselves. I would like to be able to get low adaptive regret without doing any extra work. Okay? Like you're a computer science person or computer science-y, then the lesson is to be lazy and like try to use things that you already have and hope that they give you something which is quite good. Okay, so suppose that you have an algorithm that gets low per action regret for the sleeping expert setting that I showed before, right? So you have this thing, you can make calls to this algorithm. What I want to do is, right, I want to start with the classical setting where experts are always awake. And I would like to use this algorithm, which is more general. It can handle sleeping experts. So if you think about it a little bit, this is a very natural thing to do. If you care about intervals, then for each expert J, I'm going to create some additional virtual experts. I'm going to create one virtual expert for each choice of interval. Okay? Computationally, you don't actually have to do that. That there's clever ways to get around paying something which is order t squared, the number of intervals. But for now, that doesn't matter, right? So we're going to create for each expert J, and for each interval, we're going to create a virtual expert. How is this virtual expert going to be defined? It'll be defined as follows. So if this is the interval, and let's say it's, I don't know, expert 2. Okay. So expert 2 is going to be, it's going to be this is like Z for sleeping, I guess. It'll be asleep outside of the interval. And inside the interval, its losses are going to be exactly the losses of the expert, right? So let's say L, what is it, expert 2? L, this will be T1 all the way through L to T2. Okay, so it'll be defined in this way, right? Its performance is undefined outside of the interval. And as you might imagine, we're going to consider per action regret against all of these virtual experts, right? So for any interval, and for any original expert, we have a virtual expert. And the per action regret against such a virtual expert is only going to be looking at these rounds. That's the interval regret for this particular choice of interval, right? So I'll stop in a second to make sure like that everything made sense, but just to finish the story of what bound we would get. Suppose that we had a total of K tilde virtual experts. I want K to be the original set of experts that we had, okay? So this is the bound on the per action regret that I mentioned before. It can actually be different for every A, okay, for every expert. And what we're going to do is we're going to say, okay, well, K tilde is just K times something of order T squared. The number of intervals, like T squared plus T, divided by 2. So we're going to take a log around that. So you get log K tilde. So it seems like for a very low price, you're able to get low adaptive regret, right? Classically, if we only wanted low regret over the entire interval, like the whole game, then we would pay log K and T. Right? Now we have this extra log T. The reduction makes sense. It's like, I think this particular one is kind of, the mental map is kind of easy, but.
Can you shave off this log T? Is the
I don't think so. I don't think so. Yeah, I mean, I'd have to look at lower bounds, but I think
Is
you won't entirely be able to get like log K T squared root. But
So-
whether you can reduce the price in terms of
It's okay. There was a question in the chat.
They said. they
oh, is there a chat? Sorry.
Yeah, sorry, he asked, is T fixed, is capital T fixed in advance?
Okay, that's a really good question. So for all of this, in general, we like to imagine that the learning algorithm doesn't know capital T, right? And that it might have to adapt to it.
Okay.
There are some standard tricks that, in the case of unknown capital T, you can almost always use these tricks. These are called like doubling tricks. You just run the algorithm and then you reset the algorithm. You take a guess on the number of rounds, and let's say you guess that there's 8 rounds total. When you get to round number 9, you were wrong. You reset the algorithm, and your new guess is that there's 16 rounds. This kind of thing usually can work well. I'm not going to pay much attention to that for this talk. So for the purpose of this talk, let's assume capital T is known. Right. So hopefully that. Sorry, I don't know.
That's fine.
Inside the machine. Okay, cool. Yeah. So this is one thing. I would like to make this a little bit more interesting. So when people hear about regret, one of the first questions somebody usually asks me, or for anyone, is why do we only compare against the best expert in hindsight? Well, what if I want to compare against, in the first one half of the game, I want to compare against one expert, and in the second half, I want to compare against another expert. And this might make a lot of sense because maybe I live in a world which is, stochastic, but it's non-stationary. But maybe, within different intervals, the world is stationary. And let's say the data generating distribution that's generating these losses, these loss vectors for experts, maybe it changes S times, okay? And I don't know where the changes are, but maybe if I'm lucky, I know that it changes the most S times. And then within every one of these intervals, right? It's like an after within every interval, we would like to compete with the best expert in that interval. Okay? But we want to compete with the best expert in, like, let's say the first interval, and then the second interval, and so forth, right? So we want low regret, where we sum the regret over the intervals. Okay? So, mathematically, I want to compare myself. So I have a sequence of experts that I'm comparing myself to, J1 through J capital T, and the sequence is allowed to change at most S times. It might change not at all, at most S times. Okay, and I'm going to compare my learning algorithm to the sequence. And in this case, if you, it's almost trivial. Then there is a citation for this. Apparently, it wasn't like I don't know. Maybe it wasn't realized or something. But these guys are very smart, and the only instance I could see of this reduction was like this paper, 2016. So if you want to have low tracking regret, like having in mind tracking the best expert, you have an adaptive regret bound, which holds for any interval, and you have the most S cuts, and so S plus 1 intervals, and you just take the summation over all of those adaptive regret bounds. So again, just copy pasting what we had before. Suppose you have the sleeping regret bound. This is exactly the adaptive regret bound from the previous slide. And then we're just going to multiply it by S. So sorry, it should be S plus 1. Should be S plus 1. Because if you had 0 switches, you're not going to have 0 regret, right? You're still competing with the best expert. Okay. But the thing is, I was a little bit loose over here. If you look at this bound, right? This bound is summing over the number of rounds in an interval, right? Because for each expert, for each virtual expert, it corresponds to some interval, right? And if you think about, okay, so I have S plus 1 intervals. Okay. Well, these intervals are disjoint, right? And so I really should be able to do better, right? A worst case tuning of these intervals would be that they're all roughly of equal size. And then what you're going to get over here is, instead of putting a capital T, you're going to have T divided by S plus 1, right? And that'll appear under a square root, and you'll multiply by S. So you can actually move this inside for free. Okay. And that's, I think that's, I don't remember lower bounds right now, but I think this is, I think there are constructions that you pretty much have to, yeah, I think you'll have to pay this much. Yeah. So, okay, let me check time, because there's a risk that I don't do anything new because I'm going too slow. So when did we start?
At 1:45-ish.
Yeah.
33-ish.
Okay, let me go faster. So, okay, cool. Yeah, so finally, the sleeping man study is exactly what we had before, except I've only made one change, right? So the learning algorithm, it really must, it can only take one expert. It suffers the loss of that expert. It doesn't get to take the inner products of PT with the loss factor, right? It suffers the loss of that expert. And it only gets to observe the loss of that expert. Everything else is the same. Per action regret is the same, except now I'm being very clear. It's only the loss of the expert that was selected. If you look at this and you think about the learning algorithm, it turns out because of things being adversarial, the learning algorithm will need to randomize. And what we're going to end up doing, because these ITs are going to be random, we're going to be proving high probability bounds of this quantity, right? So we would like to know that with high probability, this per action regret is not too large. Okay, so that's what we're going to do. I want to kind of recap some things that are known so far. I told you about some of these already. When all the experts are always awake and we're in the full information setting, this is the standard regret that we get. In the case when we have sleeping experts, you can improve this in this way. Okay. In the case when you have bandits, so you go into a casino, there's 3 slot machines, each one has an arm, right? And over time you want to, you want to pull an arm in each round, suffer whatever loss that you get, right? You're in the bandit setting, you don't get to observe what would have happened if you pulled a different machine in a given round. You get to observe what happens from the machine that you pulled. We have algorithms that with high probability 1 minus delta get regret of this form, right? So you have some logarithmic term. What I want to emphasize is that now you have a linear dependence on the number of arms under the square root. Okay, and basically that's because you have to explore, right? In any given round, you're only going to learn about the loss of 1 arm. Okay? And that's roughly why you get this blow up over here in terms of K. Okay? And then there's some extra small parts. What was previously known for the problem where arms can go to sleep, right? Sleeping bandits. Sorry, the arms and the experts, these are the same thing. Arms, experts, actions, currently they're all the same. So what was previously known is you can get a bound of this form on some more complicated or a different notion of regret, which is called internal regret. I wanted to give the definition of this, but for time, I won't. So some previous people, assuming an oblivious adversary, it must choose the sequence of loss vectors at the beginning of the game. And also, I think the sequence of availabilities, okay? They can get this regret bound for this other notion of regret called internal regret, okay? When they convert that, there is a conversion from internal regret to the notion of regret that I showed you over here. Okay, and that conversion picks up an extra factor of K. So the deficiency of this result is that you apparently don't need this factor of K over here. The other thing is that the result, it doesn't hold for reactive adversaries. And we would like results, as I'll explain in a second, that hold for reactive adversaries. Okay. So in terms of what's open, this is like the start of our work. So we want results that hold with high probability. As soon as you have reactive adversaries, it becomes very important to get results that hold with high probability. If you want to prove a bound on the expected regret, where the expectation is over the algorithm's randomization, the only way I've ever seen this happen in the online learning world is by first proving a high probability bound, and then doing a certain integral of the bound to get an expectation bound. Okay, so it's quite important for reactive adversaries that we get high probability bounds, and also assuming that the previous bound I showed you with the factor of K on the outside of the square root, even if it was a high probability bound for reactive adversaries, we don't want that extra factor of K, right? So these are things that we would like to fix. A very, very brief motivation. I'll give you one reason why you should care about reactive adversaries. For 2-player zero-sum games, which I hope you've at least heard of if you haven't looked at them a lot. If we want to find a Nash equilibrium, one strategy for doing so is by using what are called no regret learning algorithms. So one player is going to run a run an algorithm over experts. These experts don't go to sleep, okay? Another algorithm is going to, another player is going to run an algorithm over experts as well. And the action of one algorithm is going to basically influence the loss of the other algorithm and vice versa. And if for each of these algorithms, you have regret whose time average decays to 0, like it's like square root of t divided by t, let's say, then you're able to get a way of getting you have a strategy for computing an approximate Nash equilibrium, okay? And it's quite important here because each algorithm is influencing the loss vector of the other, and these algorithms are updating in an online way. Each algorithm is the reactive adversary of the other algorithm, okay? So there are situations like this, and there's a follow-up work, which is the reason actually we did this work that my student Juan is working on now. Actually, I guess together with Cristobal and I. And that work also requires reactive adversaries. So in general, if you can have the power of handling more powerful adversaries, then why not? Okay. So I want to give some intuition about results in the settings. So as a warm-up, I'm going to mention there's a classical algorithm called hedge, and it does what we call exponential updating. Okay. So I'm going to back up a little bit. And in the next few minutes, I want to build intuition about algorithm design for the sleeping bandits problem. So to start with, in the full information expert setting, nobody ever goes to sleep, okay? I want to update a probability distribution over experts in the following way. It's intuitive. So in round T, you look at the cumulative loss of a given expert J over the previous rounds. And then you penalize the weight of the expert in this way, right? E to the minus eta. Eta is some learning rate. It's some positive quantity. The tuning of it matters, but not a lot for intuition on this slide, okay? And then you normalize, right, by dividing by the unnormalized weights of all the other experts, right?
This we do cover in our courses.
Cool. I don't know who's been in your course.
I think they have.
Okay. Yeah.
I have.
Okay, yeah. And so hedge is an example of an algorithm that achieves that regret bound that I showed before. Right? Log k, t, squared root. Okay. Then there is a fancier algorithm that's called adapt ML prod. The cool thing about it, it may not be evident why this is useful right now, but you can get a fancier kind of bound. For any expert A, right, this is the regret of the algorithm. In the full information case, this is the dot product of PT with LT, the loss vector. So you have the square root of log t, of log k over here, but then you have this other term, which in general, the largest it can be is going to be capital T, the term under the square root. But if you have an expert where its loss is often very similar to the learning algorithm, okay, then you're going to pay much less. Okay? And this is going to be a really nice idea for the case of sleeping experts. Basically, for any expert that is asleep, its loss is not defined, but we're going to cook up a definition because the definition is just important for the learning algorithm to feed in, into its structure over here. And we're going to cook up the definition that if an expert is asleep, then its loss, or let's call it a pseudo loss because we're creating it out of nothing, is going to be equal to L hat T. Right? Which in particular, there's some cool implications of that, but let me show you more about that on the next slide. So I want to talk about this reduction idea, which imagine you have an algorithm for the standard expert setting. Experts never go to sleep. Hedge, for example. So what I want to do is I want to feed different loss vectors to that algorithm, which doesn't know anything about sleeping experts. Okay. So step one, for any expert in a given round that is available, that is awake, I'm going to set L tilde JT, the pseudo loss, equal to LJT. The loss is available, so we use it. For any expert that is not awake, we're going to do what I said on the last slide. We're going to pretend as if its loss is equal to L hat T. One cool thing about that is that, in any given round, when you're comparing to an expert that was not awake, the learning algorithm's loss is the same as this pseudo loss. And so you get 0, right? Which is what you want. You want to ignore that expert in rounds when it was not available. And that's maybe the inspiration for coming up with this idea. And then when we have these pseudo losses, right, now we have well-defined loss vectors. We can feed it to our algorithm, which only knows about experts that are always awake. right? That's all it goes about, so it's happy. And then we're going to make sure when that algorithm gives us a probability distribution over all the experts, we need to make sure that our new algorithm that we're designing, right, that it projects that probability distribution, right, onto the set of experts that are actually awake. Right, and that's what this last line is doing, right? Remember, IJT is an indicator, 0 or 1. So we're setting to 0 all weights for experts that are not available. And then we divide by the sum of the weights of the available experts. So this idea, there's some cool properties. So suppose if we're lucky, if the algorithm's loss, right, this is that base algorithm, the one that doesn't know about the existence of sleeping experts. If its loss is the same as the new algorithm's loss, then life is good, because then the algorithm's regret is going to be equal to the new algorithm's regret. I think maybe a little bit of writing might be useful here, right? But what I will do is verify this for you. Okay. So
I do have a question about.
yeah.
I mean, once you're doing this replacement, right? You're just deciding that whatever prediction was given by the by your algorithm in that coordinate, that's the pseudo loss.
Yeah.
Right? But if there's many rounds where there is no feedback from that expert, that thing is gonna start changing. And what's the what do you expect to happen? Like those weights.
Those weights. Okay, so if an expert is asleep for many rounds, then one thing I want to mention is that you only need to use the loss of an expert at the beginning of the next round.
Sure.
Okay. And the loss of the expert will always be well defined, because at the end of the current round, you'll know L hat T. And so you set L tilde JT if J is right.
But you will still be using the standard hedge on these sequence of losses, right? So yeah. What I'm saying is you would be modifying these weights in some way just to be able to get these 0 terms where they correspond, right?
Yeah. So we're going to be doing. We're always going to be running. We're going to be running hedge on the L tilde losses here.
Yeah. That's.
Yeah. So what's
I just want to understand what happens. Is this going to 0 or something? Is it?
Oh, okay. I think
is it clear what's happening in the long run?
It really depends on the relative performance, right? So if there's some experts that are always awake and have losses that are close to 0, and the algorithm, for some reason, it is not matching that. It's getting losses that are higher, and those asleep experts are going to be treated as if they're getting the higher loss. And they're going to get lower and lower weight, but it's all relative.
Okay, so it's unclear what's going to happen in the long run with those.
Yeah. I would say that if you further relativize everything by L hat T, and so replace L tilde JT by subtracting L hat T from all of them. This is a constant shift for all of them. Yeah, that changes per round.
Right.
Then you have these guys, the asleep ones that always have a loss of 0, and then the ones that are awake, that their loss is their actual loss minus L hat T. Right, which can be positive or negative, which is why I say
my increase or decrease.
Yeah. So maybe there's nothing groundbreaking about the math, right? So I'm just going to say that it turns out. So remember, in tilde land, right? Tilde land is what we have. Tilde means the algorithm that's being fed the pseudo losses, right? And it has some performance. The meaning of this, I don't know. You can unpack definitions. And in unpacking definitions, you eventually get L hat T. And just to be clear, L hat T is what I said near the beginning. It is according to the actual distribution PT, dot product with LT. Right? This is the actual performance of the algorithm. Okay. And so we have this thing that we wanted, the algorithm's loss, right, is the same as this base algorithm is the same as the new algorithm's loss. Another nice thing that happens is because of the way we define the pseudo losses for asleep experts, right? The asleep expert, it'll have the same loss as the learning algorithm. And therefore, we don't pick up, when we're comparing to an expert, we don't pick up any regret in rounds for which the expert was not available, because that expert was identical by definition, right, to the learning algorithm. And these two things together, in the case of a course bound for hedge, you can simply say, well, the regret bound that I had for hedge with experts that are always awake, using this reduction, I can still get square root of log k divided by, square root of log kt. But using that fancy adapt ML prod algorithm, for time I won't really mention much more about this, but you can replace this by the number of rounds the expert was available, right, which is better. And actually from adapt ML prod, you can even get something better than this, but it's beyond the scope of this is meant to be like the background section. So I think yeah, I wanted to give a little bit of intuition about one algorithmic idea that we're going to be using. So in the case of multi-armed bandits with experts that are always awake, but the lost sequences, for the arms are permitted active adversary. There is this idea of defining a probability distribution in the following way. So for now, I'd like for you to ignore the tilde over here. Okay, so imagine it was LIS. And imagine we had the luxury of knowing for every arm, I, right, what the loss was in any given round. Then you would do this exponential updating scheme. You would get an unnormalized weight for every I, and then you would normalize to get a probability distribution. Now in this bandit setting, right, in any given round, we only know the loss of a single expert. And so what we do is we build an estimator. This is using an idea called importance weights. Okay? And the estimator, L tilde IT, right, it has the property that if I is an arm that you did not pull in that round, then it's going to be 0 because of the indicator function. Sorry, this one with the curly brace is the indicator. And for the arm that you did pull, you're going to get LIT, the actual loss, but you're going to divide by something which is close to the probability with which you pulled the arm, plus some additional bias term. And that bias term, it's kind of technical, but is there to help us prove high probability bounds. Okay, in a sense, it's there to control the range of this quantity over here if a probability is very small. And it so happens that you get unlucky and you pull an arm, then you're gonna be amplifying your loss quite a bit. Then this gamma term here, which is tuned carefully, it helps avoid this issue. It keeps losses within a somewhat nicer range. It's still quite large range, but it is somewhat nicer. Okay. And so for this algorithm, this is old news. It's from 2015. It has a guarantee, which is roughly speaking with high probability. So log k, we have a kt. This is exactly what I showed before. I'm using the color scheme that Gergely likes to know. He likes to use this color scheme. So for his result, I use his color scheme. Yeah. So what I want to do now is start moving towards new results. So I want to start with this algorithm from before. Okay. Oh, sorry. Let me mention one thing which is very nice. I want to give you some intuition if you haven't seen the importance weighted loss estimator before. Let's suppose that we use the modified definition, which is a little bit simpler. So L, am I using tilde? So let's say L tilde IT, I'm going to say gamma to 0. We'll have the indicator that IT is equal to I. We'll have the loss, LIT, and I'm going to divide only by the probability. Okay. So why is this a good estimator? One thing that's nice about it is that it's an unbiased estimator for the actual loss. This is a basic computation that if you haven't seen before, I would be robbing you of the experience. Just do it. It's like a cute exercise. IT is drawn according to PT. If you just compute this expectation, you're going to get back out LIT. Okay. So at least an expectation, this thing is good. Because of the presence of gamma over there, it's going to be a biased estimate, but you can control the bias, right? It'll depend on gamma. And the gamma is useful because we don't just want this. We would, in a sense, like something like this to hold with high probability. And that's where the gamma is important, right? So we're gonna kind of have gamma to help, in some sense, control variance at the cost of some bias. And we can control the size of the bias. Okay. So what I've done here is, remember, right now, all of the experts are still awake. I haven't changed them. Arms, sorry, okay? So what I'm gonna do is for every expert's unnormalized weight, I'm gonna add the same term. It does not depend on I, right? Loss IS, comma S. And then this is a summation over all of the experts, right? And because we're gonna normalize the weights, I can always add whatever I want over here and over here. It's not gonna change the normalized weight. So far we haven't done anything, but in going from here to the next slide, we're gonna depart from EXP3IX. This is still equivalent to EXP3IX. We're gonna get the same probabilities. we're gonna do one more change. So when arms can go to sleep, what I'm gonna do here is, for any given round, we're gonna contribute 0 if the arm is not available. And also, in this summation over here, we're gonna contribute 0 if the arm is not available. So this is one change to these unnormalized weights, which is quite important. And the other change, which is by necessity, if an expert is not available, then IIT is 0, and they should have 0 probability, right? And then you normalize by AT is the set of available experts in round T. You can normalize it this way. These two things together allow you to prove the bound of this form. This GT, pretend like it's K for now. It's kind of more complicated than necessary for this talk. Okay, it can be smaller than K. So we get the bound, which is the log of, let's say, K divided by delta, okay? And then we have, you take the sum over the cardinality of these availability sets. In the worst case, what could this be? Well, this could be, each of these could be K. This could be T times K. But in general, right, you get something which you might view as capital T times the average of the availability set size. Right? So it could be much larger. If you were lucky and you had a game where in every round, there's only 3 experts available, but your total number of experts is like 1 billion, then the 1 billion is going to appear here, and the 3 is going to appear here. So it's quite nice. What is this really fancy upgrade that I said I wasn't going to talk about? Suppose that nominally you have a world where you have available, or that you know about, maybe 1 billion experts. But throughout the course of the game, the set of experts that ever appeared is only 1,000. The number 1,000 is what will appear here, right? So you could have what we call like an unknown set of experts, and only the experts that ever appear in the game are going to influence this GT quantity. So that's another nice improvement. Okay. So let me say, yeah, how much time is available? Because I can adaptively like maybe skip some things in order to.
About 10 minutes.
10 minutes? Okay, okay. People in this room, other than Cristobal, and if you remember, we'll talk from 2 years ago, follow the regularized leader. Have you seen this before? Online mirror descents. Something that you may have heard of. Maybe within like, I think there's a nice message for what we have here. So I'm gonna say that very quickly. There exists a really nice framework for giving online learning algorithms or algorithms for online optimization. It's called follow the regularized leader. And in the case when your set of actions is the simplex, the probability simplex, you can generally write it in this way, okay? So I'm gonna assume that we have a probability distribution dot product with these importance weighted loss vectors. That's gonna be our notion of loss. And we're gonna take the summation for any given P. We're gonna take the summation of these linear losses. And then we're gonna have a penalty function, which essentially has a form of stabilizing the sequence of predictions PT, okay? So this is called FTRL. And the thing I wanna mention is if you take the ordinary like entropy, so negative Shannon entropy, right, convex function, and there'll be a learning rate up in front. That's why the little t is over there, okay? If you do that, then you get something which is quite nice. You end up getting exactly these exponential updating, this exponential updating type scheme, okay? And in fact, you're gonna get, in the case when you use the definition that I have over here, so first, Q is gonna belong to the simplex over all experts. But then we have to fix that, right? So we're gonna do a few things. One is that for this algorithm, we're gonna use the importance weighted losses, not the ones we had before, right? So what we had before, let's see, did I put it anywhere? Yeah, actually, we can still use the standard importance weighted losses up here on this slide. But over here, for those experts that are asleep, we're gonna do a trick which looks very similar to that trick I showed before. Ignoring this, let gamma go to 0. If you're asleep, L tilde IT is equal to L hat T. There's gonna be some swap, okay? It makes it a little bit less clean, but important for high probability results, right? But the cool thing is, right, you imagine that experts who are asleep have the same loss as the learning algorithm in terms of the importance weighted losses. you feed that into this this follow the active and regularized leader framework. And whatever probabilities you get, you better make sure that you project onto the set of active experts. This thing is equivalent to the algorithm I showed you before, right? It's like you can recover that algorithm, but you can do more. You can play with that regularization function. You can use different notions of entropy, and sometimes that might give you better outcomes. I won't say much about that, but that's things in a more general framework, and you have freedom to generate new algorithms. Right? So this is like a nice idea. Yes.
Maybe like super brief, but like FTRL versus all linear descent, I mean.
You wouldn't want to do, okay, so in this particular example, online linear descent, if you're going to use a constant learning rate.
Oh, no, that's not what I meant.
Yeah.
I was saying just for maybe the students, like the distinction is like in mirror descent, you use the last loss.
Oh,
And you use this Bregman divergence to sort of keep track of what happened in the past.
Yeah,
Whereas here, you're just aggregating the cumulative losses of the whole game.
yeah.
And you may think of this phi t as a constant thing, which is just entropy, say,
Yeah.
right? But they're doing similar things, they're not radically different.
Yeah. So in the case when you have like a constant regularizer, I guess.
For constant regulars,
Yeah. So, yeah,
which is not what you want to do here, maybe.
yeah, well, so far we are doing that, but yeah.
Okay.
I think, yeah. So there's a distinction between this algorithm, which you can think of it as always remembering all the previous losses, right? And then using a regularizer, which doesn't have any memory of the previous iterative, pt minus 1. Versus an algorithm which just remembers the previous iterative and it does an incremental update using a regularizer, which measures in some sense divergence. Oh, it measures divergence from the previous iterative. Right? These are two different frameworks that in many settings could be the same. And like it's beyond the scope of this talk to get into the differences, but there is a strong reason for me preferring this framework for this particular style of algorithm with exponential updating. If you want a learning rate that could change over time. Okay, so it's so I'll mention one more this thing. So yeah, this is the one part where I actually contributed like some technical parts. So I have a bias for saying something about this, but also it's I think is it the best use of time right now. I think it's nice because it generalizes what we had before. So imagine instead of arms that are always available or not, you instead had a confidence value, which is between 0 and 1. And you can push everything through from before. An arm is only available if its confidence is bigger than 0. An expert with 0 confidence refuses to give any advice at all. An expert with confidence 0.5, they give advice, but there's going to be a weight attached to how you evaluated the regret of 0.5. For any round where there's 0.5, right? It can change every round. Okay. So this is sometimes called the confidence regret. One thing that annoys me is that like this thing is really cool, it's more general, but there's very few like applications that I've been able to think of this thing. Right. But it seems somehow it seems cool, right? But it would be cool if you could do much more with this more general framework. Right. And I'm gonna skip, I had some technical analysis related to sketching how we get this. But I'm just going to skip that and say, what we can get is something very similar, except now, instead of having over here the cardinality, of the availability set, we're going to take the sum over the confidences. Okay. So that's yeah. So this is probably a time limit. So okay. So yeah. Take offline. I want to say one more thing, because I gave a promise about, one of the cool things about sleeping experts is that you can use the sleeping experts framework, right? In every round, we have full information. We have a way to observe the entire loss vector. You can use that framework to get adaptive regret bounds and tracking regret bounds. And the question I have is like, can we do this under bandit feedback as well? So this setting, imagine that you have before you, right? You have like, I don't know, you have 5 slot machine arms, and you have a very large set of experts, and each expert is saying that they're giving you a distribution over arms. They're giving you a recommendation, a distribution over arms that they would play, okay? And you would like to somehow see that, okay, well, I don't just want to compete with the best arm, right? In some rounds, I might have a particular expert that in the first half of the game recommends arm 1, And the second half of the game, they recommend arm 3. Or they can change every round, right? It could be a very clever strategy. And I would like to compete with the best expert, not with the best arm. Because experts could be, different trajectories in arm space over time, right? And so this is a setting called bandits, because you have arms with side information coming from experts, and will allow the experts to go to sleep. Purely for now, for the reason of getting adaptive regret bounce, okay? So in this setting, we have n experts. Imagine this number is massive. We have k arms as before, maybe not so massive. And each round, the nature will decide which experts are awake, okay? But all of the actions, the arms will always be available in each round, okay? And each awake expert provides a probability distribution over arms. And ultimately, the learning algorithm, arms are available, and it wants to play a distribution over arms. If you had a distribution over 2 experts, 0.6 and 0.4, maybe weights, and they give their distributions, you can mix those distributions, right, using your weights on the experts to get your distribution, right? So that's what you're gonna do. In this setting, basically, yeah, I'll skip this. Supposing we can get bounds for the setting, you can still get adaptive regret bounds, basically using the reduction that we had before, right? We're gonna cook up. You have an original set of arms, you have k of them. And for every arm and for every interval, you're gonna create a virtual expert, which is gonna be asleep in all rounds outside of the interval for that expert. And then if you do that, you can do the same conversion that we did before, but you have to use this kind of more general setting, right? You can't just use sleeping bandits. You need something better. If you want to get this logarithmic dependence on the number of experts. And what we end up getting is this. So in the classical bandit setting, where arms are always available, if you want to get an adaptive regret bound that holds with high probability 1 minus delta, we can do that. And this is basically evidence once you have the guarantee for this, right? And the very last thing, this is the last slide. You can do the same thing for tracking regret. It's totally trivial. You just take this, you multiply by s plus 1 or s, right? The number of intervals, and now you have your tracking regret bound. And in this case, I don't know of a way to move this on the inside. We know how to do that only if you tune your algorithm with knowledge of s, the number of switches. But if you want to run your algorithm without having to know s, and you want a bound that holds for many values of s, right? Then also in the literature, right? This is actually recovering a previous result that's known using sleeping bandits. It wasn't known how to do it using sleeping bandits. Okay. So even in prior work, if s is unknown, the s is still on the outside. Yeah, but I will mention that since I mentioned that this was already known, the high probability sleeping bandits bounds were not known, but using that framework now we can pump out these other results. So it's kind of in the computer sciencey sense, it's kind of nice, right, to be able to do this. Yeah. So sorry, I'm not. Time is okay. I'm done. So you can take time for questions. I can explain things on the whiteboard if you want or anything. So and I'm here for another this week. Well, okay, mostly next week, I guess.
Next week. Well, but first of all, thank you for your help.
Question. I mean, we asked you plenty of questions during, so.
I do oh, I think that from the chat is the old.
It's the old one?
Yeah.
Okay.
Yeah. These sleeping experts bounds, right? Or sorry, there was one slide where you had just the standard hedge bound, and you compared it with I think that one. Yeah, the per action regret. On the one hand, the setting is more difficult because you have these active or awakened experts, right?
Yeah.
So the algorithm cannot be using those experts, but on the other hand, these upper bounds look better.
Yeah, they look better because one thing I didn't mention is that this is not the only notion of regret that we have when we have experts that go to sleep. This particular notion of regret, which only counts the rounds when the expert is available, it kind of naturally is going to have this benefit because the sum will be fewer rounds, right?
Right.
But there are other notions which under reactive adversaries, even under oblivious adversaries, I think, other very natural notions of regret that you might care about, it's kind of complicated. The best I can say is that under prevailing cryptographic assumptions or hardness assumptions, these other notions are hard. So here's another one, which is quite interesting. And I guess technically it's still open, although it'd be very surprising if you could get something like this. I'll try to explain it in words first. So suppose that you have K experts. You can say that, well, in a given round, if an expert is not available, I still would like to imagine the expert having some prediction. So what you can do is you can say, I'll have a permutation. So a permutation, let's say I have 3 experts. One permutation would be like 2, 3, 1. And what I've done is I've created a permutation expert. This expert, it'll predict as the first expert that is awake in the given round. So in the current round, if expert 2 is awake, you predict as expert 2. If it's not awake, you go to 3. By the way, the world is undefined if they're all asleep. The round does not exist. Okay. So you can say, how many permutation experts do I have? Well, I'm going to have k factorial 4 of these permutation experts. Right? Is the notion of permutation expert clear? Because that's the main thing that might not be clear. Right? Right? So you just have an ordering, and a given ordering will predict as the first expert in the ordering that is. So you can take the set of permutation experts, and you can use the standard bound from hedge, and you can put the log of the number of experts, and you can put the t, and you can get this regret bound over this much richer class of permutation experts. This is sometimes called the ranking regret, or the ordering regret, or the permutation regret. If you get it down on this thing, it'll also be bound on pretty much any other notion of regret for sleeping experts. It's like the hardest one, as far as I can tell. Okay. So the problem is that, like computationally, you don't want to do the naive thing of running on k factorial experts. And there are various results that say that if you could get regret, one thing I forgot to say is that in general, right, for problems where we look at regret, what we really want is the time average of the regret to be little of 1. We want it to decay to 0. Okay, the rate could be really slow, okay, but we want it to decay with 0. There are results that show that if you can get an algorithm that is no regret, whose time average of the regret decays to 0 with respect to set of permutations, then if you can do that efficiently, then that would imply efficient algorithms for, I can't remember right now, but there's various problems for which people have struggled with for a long time, right? It's not as strong as saying that this is like NP complete, right? But it's like it's close to that. It's one of these like might be one of these DNF problems. So do you, on the top of your head, do you remember
But does it have to do with randomization or is it like PRGs or?
I haven't even thought of
Okay.
in my memory, I haven't.
Or
Oh,
how do you mean
I think
learning
if RP is equal to NP, then I think you could use
Okay.
efficient. It was something like that. Yeah, and that would be surprising, right? If RP is equal to NP.
I think so, yeah.
So yeah, I'm not a complexity guy, but there.
No, we need.
Hey, you're a little bit closer, but yeah.
No, not really.
Yeah.
Okay.
But yeah, so part of the answer is that this is kind of a weak notion of regret,
Yeah.
but it turned out to be exactly what is useful for getting adaptive regret bounds, tracking regret bounds, and there's some work with my PhD student. It was the work that inspired this in a sense, and we need exactly these per action ones. So it turns out it's more useful than I thought like a year ago. Yeah. And well, one more thing I want to say. So suppose that the availabilities are not determined by a reactive adversary, but maybe they're determined by some random process, IID process. Then we can get efficient algorithms for this problem. Suppose instead that the availabilities are determined by an adversary, like a bad, nasty reactive adversary, maybe. Let's say oblivious, okay? But the losses are stochastic. We can also get efficient algorithms in this case, right? Well, with respect to this ranking. The issue is that when both the availability sets, like who's awake and when or not, and the loss factors, when both of those are adversarial, then that's where we get these hardness issues. Yeah. So, yeah, and that's why I kind of stressed in this talk that we wanted everything to be adversarial. However, we're using this notion of regret that much easier than this thing, than this ranking. So, yeah. And, yeah, so, okay,
Well, thank you very much.
Again.
If anything was interesting to you and you want references, I can give you references to like previous work, or we also have the paper on archive, so. This paper will be in stats 2024. So, yeah.